First, I would like to thank the workshop organizer to invite me to give the talk. The title of my talk is a Bayesian approach for robust and generalizable eye tracking. As we know, the goal of eye tracking is to identify a person's focus of attention, which is represented as the visual access in the 3D space and as a point of regard in 2D space. Eye tracking has many applications, including marketing, psychology, user behavior research, gaming, human-computer interaction, and medical diagnosis. For example, when we apply eye tracking to reading, we can understand readers' reading habits, and we can use eye tracking to improve readers' reading comprehension and to improve the layout of the reading materials. Eye tracking can also be applied to marketing to understand customers' interest in products and to understand their purchase decision. Eye tracking can also be applied to game, where eye movement can be used as additional input to control and navigate the game. Many different video-based eye tracking techniques have been developed over the years, and one of the approaches is the model-based eye tracking. The basic idea of model-based eye tracking is to use a geometrical model that captures the anatomical structure of the eye to analytically estimate the eye gaze from eye images. It starts with the eye landmark detection. So, for example, it detects the landmarks on the eyelids, landmarks on the iris, and the center of the pupil. Recently, additional landmarks, face landmarks, are also being used. For example, we can use landmarks near the nose, landmark in the center of the two eyes, and the landmarks on the eyebrows. Once we have these landmarks, we can feed them into the geometrical eye model, and then we can analytically compute the center of the eyeball and the center of the pupil. And connecting the center of the eyeball and the center of the pupil, that gives us the optical access. Then through a personal calibration, we'll be able to obtain the visual access. The benefits of model-based eye tracking is that it can generalize well to different subjects, and it allows natural head movement, and it does not require any training data. However, model-based eye tracking is highly sensitive to the errors with eye landmark detection. Any perturbation or inaccuracy with eye landmark or facial landmark detection could lead to significant eye gaze estimation error. So the goal of this research is to overcome the limitation with existing model-based approach while retaining its strengths. Specifically, we propose a novel approach that combines model-based eye tracking with a Bayesian convolution neural network to achieve robust and generalizable eye tracking without explicit eye landmark detection, without explicit model fitting, and even without any ground truth gaze annotation. And this is an overview of our approach. We are given training data. So each training sample includes one eye image or face image and the corresponding landmarks. We have a total of n training samples. We are also given the parameter alpha, which is a hyperparameter that specifies the prior distribution of the Bayesian convolution neural network. And we are also given theta, which is the parameter for the geometrical eye model. So given this information, our goal is to estimate the gaze G and its uncertainty sigma T. This is the covariance matrix for a testing image IT. And this is the overall flow chart for the proposed method. So the input is a testing image. We are given the training data, and we are also given the hyperparameters that specify the prior distribution of W, where W is the parameter of the Bayesian convolution neural network. And then through a Bayesian inference, we will be able to obtain the probability of PZ given the landmark probability of PZ given the input image, given the training data, and given the hyperparameter alpha. And then we can feed this into the geometrical eye model, which is parameterized by theta, to generate PG given IT, given theta, given D, given alpha. Once we have this probability, then we can maximize this probability to obtain G star T, which is the estimated gaze. And we can also compute the covariance matrix from this probability that to quantify the uncertainty of the estimated gains. So as you can see, the key equation, the key for our approach is to compute this probability. So now let me show you how to compute this probability. So you can see in this probability, it is the probability of the gains given the input image, given the training data, given the geometric model parameter theta, and given the hyperparameter alpha. It does not include landmarks, right? It does not include the parameter for the Bayesian neural network. So that's why we said that we can perform gaze estimation without explicit landmark detection, without explicit model training. However, to compute this probability, we need to first introduce landmarks. So this, why this equation can be rewritten in this format, the joint probability of gaze and landmarks. But in order to make sure these two equations equal, we have to integrate out the landmarks, right? So this basically tells us that instead of using a single set of landmarks, we're going to try many different possible landmarks through this integration, right? So this is the key equation. Instead of doing maximization, we are doing modularization. Okay, this probability can be decomposed into two probabilities. One is the PGT given ZT, and the other is the PZT given IT, given D given alpha. And this is the probability related to the geometric I model. And this is the probability that we can derive from the Bayesian convolution neural network. So we're going to talk about this later. So now this probability, okay, and this probability, in order to compute this probability, we have to introduce the parameter W for the Bayesian convolution neural network. So we introduce this W here, we compute the joint probability. But in order to make sure these two probability equal, then we have to integrate out W, right? So we introduce another integration over W. And then this probability is going to be equal to this probability. So this is again to show you that instead of obtain a point estimation of the Bayesian neural network parameter W, we are going to try different W by this integration. And this is another modularization instead of maximization. And once we have this probability, then by applying the conditional chain rule, we can decompose this probability into two probabilities. This is called the likelihood. Right. And then this is the probability, which is the key equation for Bayesian convolution neural network. This is the posterior distribution of the Bayesian neural network parameter given the training data D and given the hyperparameter alpha. As you can see that in this Bayesian approach, the parameter of Bayesian neural network is not treated as a parameter. They are treated as random variables. So now I will show you how to compute this each of these probability. First, let's start this one. So this one basically is the I model, right? So this is probability is related to the geometric model-based eye tracking. So now let's first look at the model-based eye tracking. So the model-based eye tracking, as we said before, is that we are first going to obtain the landmarks, right? The landmarks, the facial landmarks or eye landmarks. Once we have the landmarks, then we can analytically compute the center of the eyeball and the center of the pupil in 3D. And then we connect them, this gives us the optical axis. And then through a personal calibration, assuming we have the Karpar angle, then we will be able to convert the optical axis to this visual axis. So this visual axis is basically the line of sight, right? So this basically says if we have the landmarks, right? If we have the landmarks and if we are also given the parameter theta, which is including the eyeball radius and the Karpar angles, then we'll be able to analytically compute the gaze using the model-based method. So this we can generically we can write this as this. So GT equals to H ZT theta. H is the methods that we can use to compute GT from ZT and theta. So this is H varies depending on the specific model-based method. So this gives us the relationship between the GT and the ZT. This is a deterministic equation. However, we are interested in this probability, PGT given ZT given theta. And now we are going to assume that this one probability follows a Gaussian distribution, multivariate Gaussian distribution, with a mean which is determined by this function, and a covariance matrix sigma h. This covariance matrix basically captures the precision of the specific model-based method, and it is a function of the input zt as well as the nature of the model-based method. And this sigma h can be computed offline, or we can use an average sigma h for different model-based methods. So here we assume sigma h is given and theta is given. So this probability is fully specified. And then we need to compute this probability. So this is the posterior probability of the Bayesian network parameter given the training data and given the alpha. And by applying the Bayes rule, we can say this one is proportional to the product of the prior probability of W times the likelihood of W given the training data. And the likelihood of WD can be written as the product of the likelihood for each training sample, because we assume the training sample are IID. Then the joint likelihood can be written as the product of likelihood for each training sample. So now let's first look how we compute this term. So the prior probability distribution of alpha of W. So we follow the convention in Bayesian deep learning. We assume it is basically a standard scaled Gaussian distribution with a mean 0 and a scaled scalar sigma square times the identity matrix. Basically, we assume that each parameter of the Bayesian neural network is independent of each other, and they have a mean 0 and have a same variance sigma square. So this sigma is the hyperparameter, and typically it is a small value. For this study, we set it to 1. So now this is fully specified. Now we need to look at this probability. This is likelihood. So the likelihood here, this is basically the output of the Bayesian neural network, right? So given the input image, and this is the distribution of the landmarks, and given the parameter of the Bayesian neural network, we want to compute the distribution of the landmarks. And we again assume this distribution follows a Gaussian distribution with the mean and the covariance matrix. And this probability can be implemented using a probabilistic convolution neural network, where we have an input image, this eye image or face image, right? The output are two parameters. One is the parameter of the mean, right? The other for this the Gaussian distribution. Another is the diagonal elements of the covariance matrix. So we assume this covariance matrix contains only the diagonal elements. The off-diagonal elements are all 0. So given these two set of parameters, then we'll be able to fully specify the conditional probability of P of Z given I given W, right? So this is how we produce this probability. So now we have the three probabilities. We can go back to this equation to solve this probability. But then we realize in order to solve this probability, we have to perform the two integrations. One is integration over the landmarks, another integration over the parameters of a Bayesian convolution neural network. This integration is very intractable computationally because the number of the parameter can be very large, hundreds, thousands, even millions of parameters, and they are dependent on each other. So there's no way that we can analytically solve this integration, right? So what we propose to do is we're going to sample. We propose this approximate. We're going to sample, then using the sample average to approximate the integration. So we're going to sample W from this posterior distribution. So this Wi is one sample that's sampled from this posterior distribution of W. And once we have the sample, let's say we sample M, right? We get M, Wi. And then we can sum them together divided by the total number of samples. So this gives us a sample average. So this sample average is used to approximate this first integration. So now the key issue is how can we sample efficiently, because the number of parameters is very large. We cannot use the conventional method to sample. So we use the Monte Carlo MC method. But the traditional MCM method is not efficient. So what we do here is we use this what we call this is the stochastic gradient Hamilton Monte Carlo method. This method is much more efficient in sampling than the conventional method. And the basic idea here is that this method decides the next sample based on the Hamilton dynamics, which guarantees the next sample has a higher probability over the previous sample. This allows us to sample very efficiently, and the sample can converge quickly to the true distribution. So once we have samples, then we can replace this integration by the sample average. And after we rearrange this equation, we have this equation. So now we have another integral. This integral is over the landmark ZT, right? Landmark ZT. So now what we need to do is we need, and even though this follows a Gaussian distribution, we still cannot analytically solve this integration. So we're going to approximate it by the sample average again. So this time we're going to sample landmarks from this probability distribution, right? This probability distribution. And this probability distribution, so we're going to sample J is the index sample from this distribution. And this sample is, we do not need to perform MCM sampling, but this because this distribution is follows a Gaussian distribution with only the diagonal elements of the covariance matrix. So that means that each element of ZT is independent of each other. In other words, all the landmarks are independent of each other. So we can sample each landmark independently using the Gaussian sampling, right? Once we have the Gaussian sampling, right, and we're going to sample n of them. So this gives us the n set of landmarks corresponding to each parameter Wi. So we have a total of m times n samples, right? And then we can write this equation. So we have a double summation, right, are used to approximate these double integrations, right, double integrations. So once we have this equation, then we can perform argmax over this equation to obtain G star T, the case, right? So the basic idea here is that once we're going to have what m times n set of landmarks, right? And then we're going to fit each of these landmarks to the model-based approach, right? And then we're going to generate a G star ij. So this is the ij, the best ij corresponding to zt ij. So we're going to have a total of m times n G star ij, right? Then we average them. Well, we average this, right, over average them. That gives us the estimate of the G star T. So in other words, we have m times n samples of G star ij. And then the mean of these G samples give us the estimate of G star T. And also, from this m times n prediction of G star ij, we can also estimate the covariance matrix of G star. And this covariance matrix, we can compute it from the sample covariance matrix. So first we get the mean, then we can compute the sample covariance matrix. So this sample covariance matrix basically captures the uncertainty of G star. So this is sigma G star. So this is that captures the uncertainty of G star. And here, once we have G star and sigma G star, we can produce a probability map for each image, right? The probability map, and where the using the ellipse, right? So the center of this ellipse represents the case G star, and the area of the ellipse represents the uncertainty, which is computed from the covariance matrix. As you can see this here, we have different gates, right, at different locations, right? But this ellipse area varies. This one is much smaller than here. That means there's a larger uncertainty here, and there's much smaller uncertainty here, right? Okay, so now this is the overview of our method. So this is called a single stage overview of our method, right? Overview of our method. So this consists of 3 steps. Given an input image, we're going to perform 3 steps. The first step is we're going to first sample W from this posterior distribution of W. We are going to obtain M samples of W, right? And then from the IM sample of W and the input, we'll be able to compute the IM probability, conditional probability of landmarks given I and given each of the W, right? We have the IM of them. And then in the second step, from each of these conditional probability, we'll sample Z. So we're going to sample N set of landmarks, right? So that is the purpose of step 2, right? And after step 2, we have a total of M times N sets of Z, right? And then we feed each of Z into the model-based method to generate a G star ij, right? G star ij. So the G star ij. And then once we have a total, so this leads to M times N G star ij, right? Then in the third step, we average them, we get our G star T, right? Estimate case. Then from this sample of G star ij, we can compute the sample covariance matrix. This gives us the sigma G star, sigma G star, that we can use to quantify the uncertainty of G star. Okay, so this is the one stage, right? We can also extend this to multi-stage, right? So this is the first stage, the input the image, and then the Bayesian convolution neural network, and the output is the mean and the covariance matrix of the estimated gains, right? And then from here, we can generate the probability maps. So the probability map will serve as the one set of input for the second stage. In addition, in the second stage, we still have the eye image or face image, and through a convolution neural network, we can generate the feature maps. And combine the probability map with the feature map, that they serve as the input to the second stage of the Bayesian convolution neural network, which generates the H-mean and the covariance matrix. The idea is that if we keep doing this, then we expect the estimated gains will be improved progressively with smaller covariance matrix. So that's the basic, that is what we call the cascade Bayesian convolution neural network. So now I'm going to, this basically conclude the discussion of the theoretical parts of the proposed method. So now I'm going to show some experiment. Okay, first where I want to compare the Bayesian method against the non-Bayesian method. So we're going to evaluate the two non-Bayesian methods. One is the MLE, the other is the MAP. Now, the non-Bayesian method is also called the point estimation method. So each of these methods is going to, instead of a sample from the parameter of Bayesian neural network, each of these methods is going to estimate one set of best parameter for the Bayesian convolution neural network. The MLE estimate the best parameter by maximizing the likelihood. MAP estimate the best parameter for the by maximize the posterior distribution of the parameters. A Bayesian approach, instead of using one set, it samples but from the posterior distribution of the parameters. So this is the result on 4 benchmark data set. As you can see, this is for within data set evaluation. As you can see, the Bayesian methods, right? The Bayesian methods consistently outperform the non-Bayesian methods. So these two and the non-Bayesian methods. And the performance improvement is more significant for a more challenging data set. For example, for eye depth data set, the improvement is more, the Bayesian method is improvement more significant over the non-Bayesian method. Similarly, the improvement is more significant for the UT data set. These two are more challenging compared to these two data sets. An average improvement of the Bayesian method over the non-Bayesian method is about 9.5% over the maximum likelihood and 6.8% over the MAP. So this is for the within data set. And we can also do the cross data set evaluation, where we train the 3 model using the UT data and then evaluate their performance on the 3 remaining data set. So this is the result. Again, we can see that the Bayesian method consistently outperforms the non-Bayesian method. And we can also see that the improvement of the Bayesian method over the non-Bayesian method is more significant for more challenging data sets. And overall, we see an average improvement of 12%, over 12% for the maximum likelihood, and 9% over the MAP. So you can see this improvement even is higher than this improvement. So this is a within data set. This is a cross data set. So that shows you that the Bayesian method can lead to larger improvement over the point-based estimation method for cross-data set eye tracking. In order to further evaluate our method, we want to generate some special extreme case evaluation, where we add the perturbation to the MPI dataset. Right. So there are two types of perturbation, and one is the Gaussian noise. So we add a random noise to the input of the eye images, and another is a random occlusion. So we add some black square at a random location of the input eye images, and with different percentage. And here the Gaussian noise is with different amount of Gaussian standard deviation. And again, this is for the model is trained on UT, and as you can see that again, the Bayesian method significantly outperforms the non-Bayesian method under different amount of noise and a different amount of occlusion. So this study shows that the Bayesian method significantly outperform the non-Bayesian methods under the non-Bayesian method, in particular on challenge data set and under extreme perturbation occlusion with the input image. So now we are going to show the result comparison with state-of-the-art model-based method. So here I only focus on comparison with the model-based method. As you can see, so first is within data set, but cross-subject evaluation. And we compare with this one method. And this is based on the facial landmarks. It's used facial landmarks. And this is the performance of Wang's method on the eye depth data set. And this is ours. So you can see the improvement is quite significant. It's almost 3 degrees improvement, right? And this is the improvement over our method over the Wang's method on Columbia dataset. This improvement is not as significant. So this again shows that the improvement is more significant over the state-of-the-art model-based method on more challenging dataset. And then this is compared with a region-based model-based method. So this is a two method using the eye landmarks. And this is our comparison. On these two data sets, again, this is our method outperform this method. And again, as you can see, the improvement is more significant on the eye depth data set. And this is the comparison with this method, right? With this method. And again, the improvement is more significant on the UT, which is more challenging than the MPI dataset. And finally, this is within dataset. We also do cross dataset evaluation. So again, we train on UT and evaluate the performance on 3 remaining dataset. As you can see here, and this is again the region-based, right? This is the two region-based method, and the improvement is quite significant over this method for cross dataset eye tracking, almost 6 degrees, more than 6 degrees. But the improvement over this one is not as significant, and the improvement over the MPI is quite significant over this method, but not as significant as this method. So overall, we can say that our method essentially is a model-based method that significantly outperforms state-of-the-art model-based method, in particular on challenging data sets for both cross-subject and cross-dataset performance. However, I want to make a note that our method, if you look at these numbers, our method actually is worse than state-of-the-art learning-based method. This is because, first, as a model-based method, our method does not need any ground truth annotation of the case, where the learning-based method requires ground truth annotation. So this is one issue with the model-based method. Another is the training data that we use. It's basically simply just the eye image. It's unlabeled. And the landmarks that we generate for each of these training eye image from the 4 benchmark data set is by a third-party landmark detector. We apply it directly without any refinement. So as a result, the landmark detection are not perfect. So we can say compared to the learning-based method, our method is essentially unsupervised, right? Unsupervised. That's why that may explain why our method cannot outperform state-of-the-art learning-based method. So in summary, we introduce a Bayesian model-based eye tracking method that combines a Bayesian convolutional neural network with a model-based eye tracking method. Through Bayesian inference, the proposed method can perform model-based eye gaze estimation without explicit landmark detection, without explicit model training, and even without any ground truth gaze annotations. And the experiment on benchmark dataset showed the proposed method outperformed state-of-art model-based method, in particular on challenge and noise dataset, while achieving comparable within dataset performance on easy dataset. This basically concludes my presentation, and here are some related reference. And thank you for your attention.